For this video, we're going to be looking at representations of reactions, which is just pictures, and the types of questions you'll be asked, and then also types of reactions, which is related to what we did in first year, but it's a little bit different. And then that will lead us to oxidation numbers, which will take up most of our work here. So before we get to pictures of reactions, let's talk about pictures of molecules. So this is sort of just a little cheat sheet of what we'll be looking at. So if you have one atom, it will just say the atom, like H, and that's one circle. If you have a coefficient, that tells you that they're separated. So the two H's means two circles that are separated. H2 with the subscript, that means they're bonded. So here they're overlapping. Usually you'll just see them touching, but here they're overlapping. That shows you that they're bonded, which in our formula is a subscript. And then for 3H2, you have three separated H2 molecules. So the two circles are bonded, and then that happens 3 times. So you're going to see a bunch of different types of models. This is just an example of methane, CH4, and all those types of models. So you have a chemical formula, Lewis structure, ball and stick, space filling. They're all useful in their own different ways. So this is a ball and stick, and it's asking us to figure out what the molecule is. So there's a key over here that tells you what each color is worth. And all you have to do is count the number of each color. So this is an organic compound, so we'd usually put a C first. So we C, and then you count the number of carbon circles you have, which is 8. Then H is usually next. We have 11 of those. N, we have just 1. And O, we have 2. So that's just a little warm up of how to represent molecules with pictures. Now let's get into what some of the questions might be. So here's a question still based on a molecule, but also has a little reaction twist. So what this is saying is that this is the product of decomposition. So this is saying the blue spheres represent nitrogen, the red spheres represent oxygen. What was the empirical formula of the reactant? These are the products. What was the reactant? So you can count the number of nitrogens. We have 6. And the number of oxygens, we have 12. So the ratio, and this is not the molecular formula. We can't get that information from this information. So I'm just writing it like that because it's easy for me to see that now the empirical formula I need to simplify NO2. So that's going to be my correct answer. All right, here we're given the full picture, the reactants and the products. And they're asking you to write a balanced chemical equation. So we have CH4, which we have 2 of them, right here and right here. And we're going to add that to 2 H2Os. And then our products on the other side, we can see we have CO, 2 of them. And then we have H2, and we have 6 of those. So this is not wrong. It's just also not fully correct. Okay, to get the more correct answer is going to take the smallest whole number ratio. So we're going to get rid of any coefficients that we can simplify. So what you should write for the more correct answer is this. Now it's not what's represented by the picture, but that's not what the question's asking. The question is asking, write the balanced chemical equation. And you, as a chemistry student, should understand that the more correct answer is going to be the one with the lowest possible coefficients. All right, so for this one, you are given the reactants, but you're not given the products. So the question is asking you to draw the products. So nitrogen and hydrogen react to form ammonia. We have nitrogen is the blue circles, hydrogen is the white. So we have 8 nitrogens and 1, 2, 3, 4, 5, 6, 18 oxygens. So you can write out the equation, the chemical formula reaction if you want. You do not have to. I can tell by looking at this math that my oxygens are going to run out first. It looks like 180. It's 18 oxygens. My oxygens are going to run out first because I need 3 of them for each ammonia, right? So if I did 1 ammonia with 3 oxygens, and that should be bonded, another one, so I'm going to make as many NH3s as I can. Just pretend that's bonded. But now I have no more hydrogens. Okay, so I've used all 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. But I've only used 6 nitrogens. So I would draw in the other 2 nitrogens still bonded. Okay, that N2 did not react. So what that tells us is that N2 was the excess reagent and we have 1 N2 left over. Okay, so that's what this is getting at. It wants you to figure out what the ratio should be and then draw as many products as you can with the excess reagent there floating around still in solution. So here is the same basic idea. So if you want to pause this video and try this one on your own, you absolutely can. So here for nitrogen, which is blue, we have 1, 2, 3, 4, 5, 6, 7, 8. For oxygen, which is red, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. So now we have to figure out how many NO2, because that's what it says it forms, nitrogen dioxide, how many NO2s can we form? Okay, so I can look at the numbers and see that nitrogen is going to be our limiting reagent this time. So we can do 8 NO2s. Okay, and that uses up 16 of the oxygens. So our excess reagent is going to be O2. And we just have one left over. Okay, so those are the types of questions that you would be asked with these representation of reactions. It's basic reaction chemistry that you know, just presented in a different way. So now let's move on to types of reactions. Okay. So in first year chemistry, you learned about 5 different types of reaction: double replacement, single replacement, combustion, synthesis, and decomposition. And here are some examples of those, okay? We're now going to separate double replacement into precipitation and acid-base. Okay, so I'm going to talk about those in a minute. And the other type we're going to talk about is something called oxidation reduction. So the more useful for AP and for more advanced chemistry is precipitation, acid-base, oxidation reduction. Okay, so we are going to focus on those 3. Precipitation is just a double replacement where a solid product is formed. That involves the solubility rules, which we went over last class. Remember, you only need to know sodium, potassium, ammonia, ammonium, and nitrate. Okay, those are the ones you need to know are soluble. Acid-base, also known as neutralization. Sometimes you'll hear neutralization reaction. Now, we're not doing acid-base until Unit 3, but we are going to talk about it just in general with these reactions. So if you see a double replacement where water is one of the products, that's going to be an acid-base or neutralization reaction. And then the last one that we're really going to focus on is something called oxidation reduction, which is also known as redox. You'll hear that a ton over the year, okay? So we're going to focus on these 3 types. Now, precipitation and acid-base, you kind of already know because they're double replacement, which you learned last year. We just did the solubility rules last class. Acid-base, just look for water. All right, so let's talk about redox. In order to get to redox, which is going to be another lesson this unit, we need to talk about oxidation numbers, which you might also be referred to as oxidation states. So oxidation numbers or oxidation states are just something chemists made up. Okay, we're going to talk about what it means to be oxidized and reduced a little bit today, mostly in a different lesson. So here are some rules, but I'm going to go over even more rules on the next slide. So for ionic compounds, the oxidation number is the actual charge for any monoatomic ion. Meaning if it's just one atom and it has a charge, that's the oxidation number. Like if it's Ca2+, then the oxidation number of Ca is 2+. Okay? If electrons are shared in molecules or within polyatomic ions, the oxidation number is what we call a pseudo charge. It doesn't really have to do with charge. So, okay, you can think of it that way, but it's not charge. So it's the charge, quote unquote, an atom would have if the electrons were assigned to the element that hogs them more, meaning the more electronegative element. Okay, so oxidation numbers have these rules. These rules are what we call hierarchical. You have to follow them in order. Okay, so if a lower rule is contradictory, you go with the one above it. So that's why you'll see all of these, unless it's this, because they're talking about the above rules. Okay, so elements in their standard state, so that just means as an element. So usually that would mean just one, so like Al is in its standard state. Cu is in its standard state. But if it's a diatomic, like Cl, it would be Cl2 or H2. Okay, so standard state just means it's elemental form. It will always have an oxidation number of 0. We just said the oxidation number of a monoatomic ion is the charge of that ion. The sum of the oxidation numbers must add up to the charge of whatever you're looking at, or if it's a molecule with no charge, then the charge is 0. Okay, so you would add up everything to make sure it has the right charge. And then here we get into kind of how we figure this out. Fluorine is -1 unless it's in its elemental state, F2. Hydrogen is +1 unless it's in its elemental state, or if it's bonded to a metal, then it becomes -1. Oxygen is -2 unless it's in its elemental state or peroxide. Okay, so this is kind of what you would follow. And then for ionic compounds, you're going to want to take the charge that the atom would get from the periodic table unless it's part of a polyatomic. Okay, so that's where this really comes into play. So here, what is the oxidation number of sulfur in SF2? So we know that fluorine is -1 unless it's in its elemental state, which would just be F2 by itself. So that doesn't apply here. So this is -1. Now we have 2 fluorines. So we have 2 -1s. And that tells us from the rules. Sulfur is not in the rules. However, we do know that when all of the oxidation states are added up, it needs to add up to the charge of this molecule. The charge of this molecule is 0. We have no charge written, right? So S has to have a large enough charge to cancel out whatever F is. Since we have 2 -1s for F, S must be +2. So let's talk about the oxidation state of chlorine and KClO4. Okay. We'll start with oxygen because it's going to be -2. We have 4 oxygens. Okay, so that's 4 -2. So I'm just going to write -8 to make that easier on us. Potassium is a metal that has a charge of +1, and it's not part of the polyatomic here. There is a polyatomic here, but potassium's not part of it. Chlorate is just ClO4, perchlorate. Perchlorate is just ClO4. So potassium's going to keep its regular charge of +1. So now chlorine needs to balance this out because our overall molecule has no charge. So chlorine needs to be a high enough charge to get to 0. So that's going to be +7. So this one, we have oxygen, which we know is -2 times 5 is going to be -10. There's no charge on this molecule, so nitrogen needs to be enough to cancel out that -10. So it needs to be +10. However, we have 2 nitrogens here. So the actual oxidation state of nitrogen is not going to be +10. just like the actual oxidation state of oxygen was a negative 10. It was negative 2, which we multiplied by the subscript. So you're kind of working backwards on nitrogen. We need it to total up to positive 10, but we have 2 of them. So it's going to be positive 5. Okay, so that's a little bit of information on oxidation states. There will be an opportunity for you to practice more in class if you want to, if it's something new to you. So now let's go back to the types of reactions, and we'll be going back to redox in another lesson. The 5 types of reactions, this is the same slide that I had before, except I took away the examples and added stuff about redox, because we care a lot about redox in chemistry. So double replacement is never redox. So if you ever see a double replacement reaction, you don't have to even figure out the oxidation numbers. It's never redox. Single replacement always is, because single replacement always has at least one element in its elemental form, and then it forms a compound on the other side. So it changes its oxidation state. Combustion, same thing, because oxygen, O2, is always in elemental form in combustion. So synthesis and decomposition, if you're talking about redox, those are the only ones you have to actually look at the oxidation states for. All right, so now we'll kind of take our information and put it into reactions. And like I said, we're going to go a lot more into this in another lesson, but for right now, we're just doing intro. What element is oxidized or reduced? Okay, so what you do for that to figure it out is figure out the oxidation state of each element. So here, Al is 0, it's in its elemental state, and then over here, Ni is 0. Chlorine's going to be -1 in both of those. So then that means here nickel is going to be +2 and aluminum is going to be +3. Oxidized means the oxidation number goes up. Okay, we'll talk about what that means in terms of electrons on a different lesson. Okay, because that's where it kind of gets confusing. Right now, we don't have to worry about that. We're just looking at the numbers. Which one of them went up? Chlorine stayed the same. Nickel went down. Aluminum went from 0 to +3. So that means aluminum is oxidized. So now I'm going to do the same thing, except this time I'm looking for which element is reduced. So here we have hydrogen in its elemental form, iron in its elemental form. Oxygen is -2, so that means we have -6 here. So iron gets +3 because we have 2 of them. And then we have -2 and +1 here. So which one goes down? Oxygen stayed the same, hydrogen went up, and iron went down. So that means iron is reduced. So here's another type of question. So which reaction below is not an oxidation reduction reaction? Okay, so what I would do here is look for the types I know are always redox. So combustion, we have combustion number 5. That's not going to be the answer, okay, because we know that combustion's always redox. Single replacement right here, that's not going to be the answer. Single replacement right here, not going to be the answer. And as I'm doing that, oh, this is also single replacement. And as I'm doing that, I noticed that this one is double replacement. Double replacement is never redox. So that's got to be the answer. So you could have just found that one if you noticed it, or use process of elimination. Either one of them is fine, as long as you get the right answer. So now I'm just going to give you a bunch of reactions that I think you should probably pause the video and answer them on your note sheet, and then come back and check your answers and bring any questions that you have to class. So this is precipitation. We can go into what it is, but this is going to be the precipitate. This is going to be the solid based on our solubility rules. This one is redox because it's single replacement. So remember, precipitation and acid-base are double replacement. They're different breeds of double replacement. Okay? So the next one is acid-base because it has water as a product. This one is redox. Now it's synthesis, which we said is sometimes redox, right? So if you want to, you can do the oxidation numbers real quick. It's pretty easy. We have 0, 0, +1, and -1. So you can see that they do change their oxidation numbers. And next lesson we'll get into more of what that means. But here you can just see they don't have the same numbers, so it must be redox. This one is acid-base because we have water as a product and it's double replacement. And then this one is precipitation. And that's going to be the precipitate.